Welcome everyone. During this lecture we're going to be discussing various topics related to an object undergoing circular motion, including the relationship between radians and degrees, conversions between radians and degrees, arc length, angular position, and angular displacement. We'll examine the relationship between arc length and angular displacement. We will introduce an arc length and angular displacement application. We'll define average angular velocity and average angular acceleration. We'll introduce the conversion between revolutions per minute, which is otherwise known as RPM, and radians per second. And finally, we'll conclude with a rotational motion application. We'll begin by defining the radian unit, and then we'll establish the relationship between radians and degrees. The process begins by introducing a circle with a radius of 1 unit. Now the choice of unit is not important. The radius could be 1 meter, 1 inch, 1 foot. The unit is irrelevant, but for our purposes we'll assume that the unit is the meter. So here's a circle with a radius of 1 meter. Next, we're going to note that the circumference is related to the radius through the following equation. The circumference simply equals 2 pi times the radius. Now, if we introduce a radius of 1 into this equation, then the circumference of this circle simply equals 2 times pi. And if we enter 2 times pi into our calculator, the result equals 6.283. Next, let's imagine wrapping a tape measure around our circle, and this is a tape measure that measures meters, and we'll use the tape measure to mark the 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, and 6 meter locations around the circumference of that circle. If we do so, the result will look like this. So, the length of the arc between 0 and 1 is 1 meter. The length of the arc between 0 and 2 equals 2 meters, and so forth. The length of the entire circumference equals 6.283 meters. Now, let's highlight the arc between 0 and 1. Next, we'll extend 2 line segments from the origin to those 2 locations. So here's the first, and here's the second. By extending these 2 lines, we have created an angle. And we'll note that angle as theta. As it turns out, this angle is defined as 1 radian. And notice that the definition corresponds with this line's location along the unit circle. So at 1 meter, we have defined 1 radian. If we extended a line out to 2 meters, then the arc formed by that line with respect to the 0 line would be 2 radians, and so forth. And so this angle is defined as 1 radian. We will now derive the relationship between radians and degrees. In other words, how many degrees are occupied by an angle whose measure is 1 radian? We can determine this relationship by equating 2 proportions. In other words, the number of radians occupied by our angle divided by the total number of radians within the circle must equal the number of degrees occupied by our angle divided by the total number of degrees contained within the circle. Now, the number of radians occupied by our angle, in this case, equal 1. So we have 1 radian, and the total number of radians contained within a circle equal 6.283. This must equal the number of degrees divided by the total number of degrees within a circle, which of course is known to be 360 degrees. If we multiply both sides by 360, we obtain 360 divided by 6.283 equals the number of degrees. And if we enter these values into the calculator, the result equals 57.3. And so we've established the relationship. 1 radian equals 57.3 degrees. And we will use this relationship anytime we need to convert between radians and degrees, and vice versa. We will now explore the relationships between the primary angles measured in degrees and their radian counterparts. Let's begin by introducing the unit circle once again. In this circle, the radian measurements are designated in red, while the primary angles measured in degrees are designated in black. Let's label the angles in degrees. This first mark indicates a 30-degree angle. Next is a 45-degree angle, a 60-degree angle, and so forth. There's 90 degrees. This would equal 135 degrees. Of course, halfway around the circle corresponds to 180 degrees. Here's 225. Here's 270 degrees, 315 degrees, and of course all the way around the circle corresponds to a 360-degree angle. We will now establish the relationship between a 30-degree angle and its radian counterpart, and we'll apply a method using proportions similar to the method that was used earlier. And so the proportion would look something like this. 30 degrees divided by 360 degrees must be proportional to its radian counterpart divided by 2 pi radians. Of course, the entire circle consists of 360 degrees as well as 2 pi radians. Now let's note that 30 divided by 360 can be reduced to 1/12. That would equal the radians divided by 2 pi. Next, we'll multiply both sides by 2 pi. And that'll result in 2 pi divided by 12 equals the radians. And, of course, 2 goes into 12 6 times. And the final result looks like pi over 6. And so 30 degrees corresponds to pi over 6 radians. Now, we could reduce this to a decimal value, but typically we leave the radian measurements in terms of a fraction of pi. If we apply a similar procedure to the remaining angles, we would obtain the following results. 45 degrees is 1/8 of a circle, and 1/8 of 2 pi equals pi divided by 4. 60 degrees amounts to twice 30 degrees, and so 2 times pi over 6 would equal pi over 3. 90 degrees equals 3 30-degree angles. If we multiply pi over 6 by 3, we obtain pi over 2. and so forth. 135 degrees equals 3 pi over 4 radians. 180 degrees is half of a circle. A full circle, of course, is 2 pi radians, so half of that would equal just pi radians. 225 degrees would equal 5 pi over 4 radians. 270 degrees equals 3 times 90, right? And 90 degrees just simply equals pi over 2. 3 times that would equal 3 pi over 2. 315 degrees equals 7 pi over 4. And finally, we know that 360 degrees equals 2 pi radians. We will now introduce a couple conversion examples. In this example, we would like to convert 135 degrees to radians. This is just a straight conversion. We're looking for radians. We're given degrees. And of course, the connection between radians and degrees is 57.3. If you recall, earlier we established that 1 radian equals 57.3 degrees. So we'll introduce 57.3 degrees in the denominator, 1 radian in the numerator. Of course, the degrees cancel, and our answer just simply equals 2.356 radians. In the next example, we're going to convert 489 radians to degrees. Again, very straightforward process. Degrees in this case would equal 489 radians. And we'll apply the same conversion factor that was used earlier. We know that 1 radian equals 57.3 degrees. The radians cancel, and if we enter these values into our calculator, the result equals 28,020 degrees. We will now define arc length, angular position, and angular displacement. And to do so, we're going to consider the following diagram. We will now represent an object traveling along a circular path. Let's assume that the object begins its journey at this location and ends its journey at this location. Also, let's note that this circular path has a radius of r. So the radius will be described as r. Let's also mark the object's initial position as I and its final position as f. Now, by traveling between its initial and final positions, this object has covered a certain amount of distance that is represented by the length of this arc. So let's highlight this arc. we'll note that the length of this arc is S, and once again, S represents the amount of distance covered by this object. S is called arc length, and the definition of arc length states that it is a measure of the distance traveled by an object along a circular path. As we noted, the symbol for arc length is S, and the units are meters. Next, we're going to define the object's location by extending a line from the origin to the object, and then we can designate the angle that is subtended between the x-axis and the line as theta initial. We can extend another line between the origin and the object's final location and designate that angle as theta final. These angles are known as angular positions, and we will now introduce the definition of angular position. Angular position is a measure of the angle subtended by an object traveling along a circular path. Relative to the positive x-axis. The symbol for angular position is theta, and the units are radians. We can now define angular displacement. Angular displacement is a measure of the change in an object's angular position. In other words, angular displacement measures how much change there is between the initial and final locations of an object. The symbol for it is delta theta. The equation for it is simply theta final minus theta initial, and the units are radians. Let's indicate the angular displacement for the object that we were just discussing. Here's our object, and the change in angular position is just a measure of the angle subtended between the initial and the final locations. And so delta theta looks like this. Okay? Delta theta just measures the angle between the initial and the final positions. We're now going to derive the relationship between arc length and angular displacement by noting that the ratio of arc length with respect to displacement will equal the ratio of the arc length for the entire circle with respect to the angle subtended by an entire circle. That relationship can be expressed as follows. Again, the arc length divided by the angular displacement would equal the arc length of the entire circle, which of course would be equal to the circumference, divided by the angle subtended by an entire circle, which of course equals 2 pi. Now the circumference just equals 2 pi times the radius. So if we make that substitution, the result looks like this. Now, let's note that the 2 pi's cancel, and if we multiply both sides by delta theta, we obtain S equals R times delta theta. That is the relationship between arc length and angular displacement, and it's a very important relationship. Now, one thing I would like to note is that when we use this relationship, we are obligated to enter delta theta in radians only. Degrees cannot be used in this relationship. So delta theta must be entered in radians only. We will now evaluate the following example. In this example, an object traveling along a circular path with a radius of 3 meters undergoes an angular displacement of 125 degrees. Determine the object's angular displacement in radians. So let's take inventory of what is known. First of all, the radius equals 3 meters. The angular displacement, which of course is noted by delta theta, equals 125 degrees. However, this value must be converted to radians as we noted earlier. So let's do that right away. We know that 57.3 degrees equals 1 radian. The degrees cancel, and the value for delta theta equals 2.182 radians. And so by conducting this conversion, we've also answered part A. So the solution to part A is delta theta equals 2.182 radians. In part B, we would like to determine the distance traveled by the object. Now, distance is denoted by arc length, which is symbolized by the letter S. We need to find S, and of course S just equals R times delta theta. The radius is given as 3. Delta theta was just calculated as 2.182. And if we enter these two values into our calculator, the result is 6.545 meters. We will now introduce the definition of average angular velocity. We will now introduce the definition of average angular velocity. Average angular velocity is a measure of an object's angular displacement with respect to time. And so the components of average angular velocity are angular displacement as well as time. The symbol for average angular velocity looks like this. We use the Greek letter omega, which is a rounded version of the letter W. And let's make sure that we use the rounded version when describing angular velocity. The equation for average angular velocity looks like this. Again, the components are angular displacement, which is represented by delta theta, as well as time, which is represented by delta t. From this equation, we can extract the units. Delta theta is expressed in radians, and delta t is expressed in seconds. And so the units for average angular velocity are just radians per second. Let's now define average angular acceleration. Average angular acceleration is a measure of the average rate at which an object's angular velocity is changing with respect to time. And so the components of average angular acceleration are angular velocity as well as time. And also let's take note of the fact that angular velocity has to change in order for average angular acceleration to exist. Now the symbol for average angular acceleration is the Greek letter alpha, which looks like this with a bar on top. The equation for it looks like this. Alpha bar equals the change in angular velocity. Now we just noted that angular velocity is represented by the Greek letter omega. So the change will be represented by delta omega with respect to time. Now if we expand delta omega into omega final minus omega initial, we have then the other form for average angular acceleration, which looks like this. And the units are, well, omega is expressed in radians per second. And time is expressed in seconds. And if we just conduct some algebraic maneuvering, the resulting unit is the radian per second squared. Now let's go back for a moment and take a look at the units for angular velocity. As you can see, the units are radians per second. However, sometimes this variable is represented by units called revolutions per minute, or RPM. Whenever this occurs, we're going to have to convert RPM to radians per second. So in the next example, we will derive the conversion factor between revolutions per minute and radians per second. Let's present it as an example. In this example, we're going to convert RPM to radians per second. So it starts by expressing the desired unit, as always. We're looking for radians per second, and we're starting off with 1 revolution per minute. We'll express the RPM as a rev over a minute. Okay, RPM is a revolution per minute. Now we know that 1 revolution equals 2 pi radians. And we also know that 1 minute simply equals 60 seconds. If we enter these values into our calculator, the result is 0.1047. Therefore, 1 RPM simply equals 0.1047 radians per second. And this is a very useful conversion that we can rely on any time angular velocity is expressed in terms of revolutions per minute. We will now introduce an example involving the quantities that we've discussed thus far. Starting from rest, an object traveling along a circular path with a radius of 1.5 meters reaches an angular velocity of 60 revolutions per minute in 30 seconds. At this time, the object attains an angular displacement of 5,400 degrees. In part A, we would like to determine the distance traveled by the object in the first 30 seconds. Now, distance is denoted by the letter S. But before we begin, let's take inventory of what is given within the problem. Now, the words starting from rest imply that the initial angular velocity equals 0. And of course, initial angular velocity is represented by omega initial. Omega initial in this case equals 0. The radius of the path is given as 1.5 meters, and also it's noted that the object attains an angular velocity of 60 revolutions per minute in 30 seconds. This is represented by the object's final angular velocity, which is represented by omega final. So omega final equals 60 revolutions per minute, which could be abbreviated as RPM. Now, as we just noted, RPM is not an appropriate unit, and therefore it must be converted to radians per second. In order to convert RPM to radians per second, we can note that 1 RPM equals 0.1047 radians per second. The RPM disappears, and if we enter these values into our calculator, omega f just equals 6.282 radians per second. The time is indicated to be 30 seconds. And the angular displacement equals 5,400 degrees. Now, as we mentioned earlier, degrees are also an inappropriate unit. They have to be converted to radians. Now, the question now is, which variable represents angular displacement? And as we discussed earlier, the answer to that is delta theta. Delta theta is given as 5,400 degrees. And that needs to be converted. Now, we know that 57.3 degrees equals 1 radian. And if we enter these values into the calculator, the result equals 94.24 radians. We can now proceed toward finding S. Now, earlier we established an equation between arc length or distance and angular displacement. The equation looks like this: S equals R delta theta. In this problem, the radius equals 1.5 meters, and we just determined the value for delta theta as 94.24 radians. The result equals 141.4 meters. In part B, we need to determine the object's average angular velocity in radians per second. Now, the symbol for average angular velocity is omega with a bar, and the equation for omega bar is simply delta theta over delta t. We noted earlier that average angular velocity equals the angular displacement divided by time. The angular displacement was calculated earlier, right here. It equals 94.24 radians. And the time equals 30 seconds. The result equals 3.141. And the units for average angular velocity are radians per second. In part C, we would like to determine the object's average angular acceleration in radians per second squared. And by the way, the word squared was missing earlier, so make sure you add it to your notes. Now, average angular acceleration is represented by alpha with a bar on top, and the equation for it is just the change in omega with respect to time. The other form looks like this. The change in angular velocity is simply omega final minus omega initial divided by delta t. Now, omega final was calculated earlier as 6.282. Omega initial was designated as 0 because the object started from rest, and the time equals 30 seconds. By the way, note that there's a big difference between the average angular velocity and the final angular velocity. The final angular velocity equaled 6.282, whereas the average angular velocity equals 3.141. If we enter these values into the calculator, the result is 0.2094. And the units for average angular acceleration are radians per second squared. And that completes this lecture.